The last thing in your notes should be, let me see what color I'm in here. See if this works. That's the wrong color. Let's erase that and try again. Let me pause. Okay. Hopefully Trace is worth all the trouble we've gone to make sure he's got this video. Yes, I am recording, so he will hear it. You should have in your notes f of x, or do we do a? Okay. F of a plus h minus f of a over h. Why was it just h? Because what did we have before that? A plus h minus h, right? So in essence, you will get to know this particular ratio really, really well during this chapter and throughout the course. This is one of those things you don't want to ever forget because they actually put AP exam questions. And you should hope to see this, and you will learn to recognize what you're seeing to know how to answer the question without doing any work, okay? So you want, as much as this thing might cause you to say words your grandmother doesn't like to hear, you will be glad you know it when you take the exam, all right? So, what did we say this is? The average rate of change of the function between the 2 points that are related to this problem, right? Now, we used h, which is an abstract thing, and what does h represent? And if you can't tell from your notes, you don't take good enough notes. Tell me. Did you say height? Okay, well, you need to check your notes. That's right, how far apart the two x-coordinates are, right? So it's the distance in x-coordinate, in horizontal terms, between the one point I'm looking at and the other point I have, okay? Now, the reason we use h is that ultimately, and we talked about, we were heading in this direction yesterday, and you were all looking at me like, dear God, what is she talking about? And a lot of our notes and discussion will be largely theoretical, and then when we do the examples, you're going to be like, wow, why do we have to go through all that? Because in calculus, you have to know the theory behind what you're doing, because otherwise you can't answer the questions as they'll come at you, okay? All right, if h is the distance between the 2 points I'm using, and where did we get those 2 points yesterday? And I will sketch this picture here similar to what I had yesterday. I don't remember exactly what I had, but I know we were working with the parabola, y equals x squared. This is a terrible sketch, but just work with me. All right, and then we had this line that went through that way. So what does this picture have to do with this formula?
The 2 points are the intersections.
That's right. The 2 points are the intersections between the line and the parabola, right? Okay. So we also talked about a tangent line, which would, instead of intersecting the curve twice, would only intersect it once, would look something like this line. Yes? All right. So I mentioned, and we'll see how closely you were listening, that the tangent line tells you exactly what happens at the point, but then what happens?
As it gets farther away, it becomes less
right. The further away I get from that x-coordinate in either direction.
Teachers, please send 81 to 120 down to top deployment. That's 81 to 120.
See, Trace, you get to enjoy all that crap even though you're not here. All right. So the further away I get from that center, the point where they intersect, the less the line tells me about what the function's doing. Yes? Okay. Well, so that being the case, looking at our formula, think for just a moment. We'll see if I can tease this out of you. The h is the distance between the 2 points, right?
Yep.
So ideally, how do I want h to be? Well size-wise, how big of an h would I like to have?
Small.
Who said small? I heard it. Wasn't that Preston? I thought it was Preston. Okay. I want h really small. What would a really small h, and I'd love to hear from somebody I haven't heard from yet, whoever you are that's been quiet, what would a really small h do for me that would be a good thing? Okay, the microphone can't hear you muttering, and neither can the people behind you.
The smallest and easiest rate of change to find.
Smallest and easiest rate of change. I think you're thinking in the right direction. I don't think you're saying it the right way. Anybody else? What would be the advantage of a really small h in this scenario?
Easier to divide by whatever. I don't know.
Okay, let's rewind. What did we just say? What you said it, so I know you remember me saying it, but maybe you're not processing the full impact of what you're saying. The further away from the x-coordinate of the point of intersection with the line, with the curve, the less accurate it is. So I ask again, what would a really tiny h do for me? It's going to make my approximation more accurate, right? So in a perfect world, what would be the most possible accurate value of h? 0. I'd like to get really, really close to 0, or in a perfect world, I could let h be 0. Got it? Okay. Store that in the back of your mind, okay? Now, for our purposes, we would rather know, well, let me ask you this. Which would be more useful to you when, let's say we've had our first test. You come in the next morning. I didn't text you your grades yet. Well, generally, if I haven't texted you your grades yet, that either means I had a really late night grading and or the grades weren't really great and I didn't feel like texting them to you. Okay? So if you haven't gotten your grades yet, by the time you walk back in class the next morning, what is the first thing on your mind?
We failed. That we didn't do too.
What do you want to know individually? What you made, don't you?
Yeah.
Okay? Well, what if I said, well, the class average was an 82? How much does that do for you?
It kind of makes it all feel okay. It just makes us.
It should really do absolutely nothing.
Oh.
Because theoretically, the top grade could have been 100 and it could be you that I'm speaking to, right? You see what I'm saying? So knowing an average kind of gives you a sense of things, but it doesn't really tell you anything specific. Am I right? Okay. So in a perfect world, what we would rather have is instantaneous. And we're going to call it speed because a lot of the application that they use in the course throughout to help you understand a lot of these relationships is particle motion, or like something moving at a particular rate using a particular function. And so obviously what would the instantaneous speed be? It would be the speed at some particular point in time, right? So in this picture where I'm using curves and lines with the lines approximating them, that point at which I'm interested is probably that point of intersection. Does that make sense? So that's kind of the gist of where we're going. All right. And again, and I will read to you what the book says to tie in what I just said so you don't think I'm just talking off my crazy head. A moving body's instantaneous speed is the speed of the moving object at a given instant of time. The major issue is how to compute this speed since the elapsed time must be 0. Well, speaking in terms of analogy of speed, or in the case of speed, looking at what we've talked about so far, what would that relate to? What are we talking about if the elapsed time must be 0? What were we just talking about? H, right?
Yeah.
So H has to be 0. What's wrong with H being 0 in our formula? You can't divide by 0, right? Okay. So if you are given, find the speed of the rock at a specific time, you're going to use your formula, whatever the function you're dealing with, and then you're going to get your value, okay? And that sounds really abstract, but I'm going to come back and do examples in a few minutes, okay? All right. Now, this chapter, as I told you yesterday, and I'm going to go ahead and get a clean screen up here. As I told you yesterday, this chapter is about limits. And limits blow people's minds, but they're really basic and simple in terms of computing most of the time, okay? Sometimes you have to do some algebra to clean it up to where you can actually compute it, but it's the doing of the problems is not the hard part. It's the understanding the concept that seems to be the issue. So I'm going to give you a really quick and dirty version of limit. I'm not going to go into the details, and if your book is open and you would like to look, and if it's not, make yourself a note to see page 60 at the bottom, because I've tried to explain that before, and no matter how eloquently I do it, people don't really seem to get that much out of it, okay? All right, so this is the definition of a limit. Okay. Now, I will also tell you that this chapter, this concept, is one of those areas of study that sort of takes time to soak in. You are not used to that. You are used to understanding something, and if you don't understand, you are used to asking enough questions until you understand. But in this particular case, in all likelihood, your best approach is just to be patient and wait to understand, okay? You'll be able to do the homework, but you won't really have a sense of what you're doing, okay? That's the norm. If you do, great. That says great things about you. All right, the limit. Okay, so I'm going to read to you directly what the book says in case your book's not open, but then we're only going to record the parts of it that you really, really, really need to know for our purposes. The definition itself says, assume f, and that's the italicized f as in function notation f, is defined in a neighborhood of C. All right? So that's some x value. Okay, C is just some particular x value. All right? So I'm going to write just the phrases that matter. F is defined.
Teachers, please send number 121 to 160 down to laptop deployment at this time. That's number 121 to 160.
The function is defined in some neighborhood, and your book says of C, but I'm going to say containing C. And we don't normally use the word neighborhood. It's not a very mathy word, not by textbook standards, but you will hear a lot of professors use such language. Neighborhood meaning in the area. What do we normally call an area of a function? I'll give you a hint. It starts with an I. The what? Did you say it? Interval. Oh, you said interval. I thought I heard somebody over there say it. Interval, right? It's going to be a long Tuesday, I can just tell already. All right, containing C. And as we said, C is some x value, all right? And then I'm going to make a parenthetic note here. C and L are real numbers. All right, I'm going to do that last little swipe. So I'm going to put dot, 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 and if you want to see the details, you can go back. And I'm actually going to write this notation, but you're not going to really understand it, but that way you'll have it in your notes for later reference, and hopefully at some point something will click, but for most students it really never does. All right, so f has a limit. What's f? Function. Has a limit, or has limit, it doesn't even say a, has limit L, and that's capital L, because not everything has a limit, okay? And that's something we'll spend time exploring in this chapter. As x approaches C, if and I'm going to read what the words say, and then I'm going to write the symbolic notation and let you just say, okay, that's that part she was talking about. If, given any positive number epsilon, there is a positive number delta such that for all x, 0 is less than the absolute value of x minus c. Now let's pause right there, because y'all should know what that means when you see it. And we actually talked about it a little bit last year, but maybe not enough for you to actually be able to call it this morning. What is the absolute value of a difference of two things? What does that tell you? That's right, it does. That is the distance, the straight line distance, typically horizontally speaking, and we are in x, so that takes care of that, between x and c, right? So what have we said so far? And the absolute value, remember, is distance by definition. The absolute value of that difference has to be what? Not just positive, yeah, greater than 0 specifically, right? And not everybody has a clear definition of positive, which is why I wanted to say that. All right, so then that has to be less than sigma, which is just another variable. So that implies that the absolute value of f of x minus L. All right, now let's pause right there and see what that part means, because this part really matters. The sigmas and deltas will blow your mind, so we're not going to get too heavily into those, but I do want you to understand the components you can understand. What is f of x? Specifically, in a point, the y-coordinate, right? The point would be x, f of x. We talked about that yesterday. So this is the y-coordinate, the difference between y and L, right? Absolute value. So in other words, the distance between them has to be less than epsilon. That is called the epsilon delta definition of limit. You can make a 5 on the AP exam without ever fully grasping that. Okay? But we will come back to it later in other contexts, and I'll keep trying to nudge you towards understanding it. Not everybody does, and it's not necessary for survival. All right? So we write, and this is the way it should be written. You write LIM as that's the abbreviation for the word limit, okay? And underneath it, you're going to write X and a little arrow and C, okay? Of the function, and that's how you read this. So you write little LIM over X arrow C. That means the limit as X approaches C of this function is L. Now, remember the picture? Well, in fact, let me sketch it back here again, okay? So I'm just going to put a parabola here. Not a terrible parabola, but we'll keep it simple and stay with our good friend y equals x squared, okay? All right. If I pick a point, let's say I want to know the limit as x approaches 2 of x squared. And sometimes you'll see like g of x or f of x, like the name of the function, and sometimes they will actually list the function here. If there is more than one term, that function will be in parentheses. Okay? So we want to know the limit as x approaches 2 for this function. Okay? Well, if I get really, really close to 2, well, let's rewind. On this function, where would that put us? If I go out to 2, what are the coordinates of that point? 2, 4. Okay? Now you see why I'm keeping it simple. All right, so we're looking at the point 2, 4.
Teachers, please send number 161 to 180 for laptop deployment at this time.
Don't you think after about the third time we could just quit saying the for laptop deployment? I think we got that part.
Doesn't she mean it 2? I said twice.
Okay. So, why? What's wrong, Will?
Doesn't she mean 200? Can you count?
Okay. I can't solve all the world's problems. I'm really just trying to teach y'all limits here. All right, so the limit as x approaches 2. I probably could if they'd give me the power, but I don't have it, so what's the point? All right, so we know the point 2, 4 is on the function, right?
Yes.
Well, if I get really, really close, like if I'm tracing the curve, and I'm going to switch colors.
Teachers, please also send 180 to 200. That's 161 to 200 to laptop deployment at this time.
They heard you, Will. All right. It didn't matter enough for me to call them and say, hey, didn't you mean this? I figured they'd figure it out. That's what they do. All right, so let's just say I'm riding along this train track, and I pause right here. Now, I've already passed the point 1, 1, and I'm heading towards the point 2, 4. Yes? The closer I get to the point 2, 4, the closer my y-coordinate has to get to what?
4.
Why?
Because it's having
Because that's how it works.
Yeah.
Because if the curve is rising towards that point, the y-coordinate has to get closer and closer to the actual point value of 4, right? Okay? What would happen if, for some reason, I'm coming from the other direction? Let me pick a color that'll work. I'll go with red here. All right, so now I'm riding the track from the opposite direction. So let me come at it this way. Now what happens as I come at it from the other side? I'm still getting closer to 4. I'm starting from higher numbers and falling towards 4 as opposed to climbing towards 4. Yes? Okay? So that's what this means. So what that tells me then is that the limit as x approaches 2 of x squared is 4. Now, This is going to sound like a ridiculously stupid question, but I must ask it.
Okay.
How did we know that it had to be getting close to 4? Okay, we are not, I'm trying to think of the monks. We're not monks, so we don't mutter our answers to God. We're talking to each other, okay? So let's try that again. How do we know that it was 4 we were approaching there? It's the point. That is not very mathy. Because what? The coordinates of the point are 2, 4. How did I know the coordinates of the point were 2, 4? Because it's a parabola. Because 2 squared is 4. That's what the function gave me there, right?
Yes.
Okay. So if I approach it from either direction, for the curve to be smooth, that has to be true. Yes? Okay. You just learned your first technique for finding limits. The first technique for finding limits, and you always do this algebraically, especially when you don't have the graph and it's a weird-looking function, is you plug the value in that you're approaching. Because the limit as x approaches c, c is a specific value of x. So if I want to know what y is as I get really close to it, I plug that number in to get my y. That is all that you're going to be doing. Isn't that easy? Okay. Now, let's look at a very important function, well, really a very important limit of a very important function. The limit, and I'm writing it really big because this is pretty huge. And your textbook, if you have it open, should already have this boxed in ink.
Yeah.
If it is not yet done, take care of that now. Because if I wrote this calculus book, I would put like little glittering lights or something around that. Like where when you turn the page, it'd be like a Harry Potter book. It'd be like, know this, okay?
Ask some questions, she'll be happy.
All right, so sine x over x equals 1. Now, they're telling you this. They, as in the authors, okay? And as suggested in figure 2.1. All right, in your book, if you have it open, and if you don't, it's not a huge deal. You can graph this on your calculator at some point if you're curious. They have it graphed for you over in the margin on page 60, figure 2.1. Okay? And they give you the graph, they give you a table, and then they tell you. All right? But now let's just look at this function like the good pre-cal students that we are today. We're not yet good calculus students because we're just learning how to be calculus students. But looking at this function, why can I not just plug x in here? Because as x approaches what?
0.
Why can't I plug 0 into this function?
Because
Because you're dividing by 0,
yeah.
right? Okay. What is the sign of 0? What is the sign of 0? It is 0, yes? I wanted a more hearty response since we just reviewed our trig. What is the y-coordinate at the angle 0? It's 0. Yes, the x-coordinate would be 1 there. Okay, so the sign of 0 is 0, right? So if is the sine graph continuous?
Yeah.
Where? Everywhere, right? So at 0, it's still continuous, all right? On your paper, over somewhere to the side, sketch the sine graph right quick. Not nowhere near accurately, just a quick little sketch centered on the y-axis. That's why I said sketch. And for those of you who are looking up here hoping that I draw it so you don't have to remember it, this would be one period of the sine function, roughly sketched. Yes? Okay. If I use the writing the function track analogy, if you hop on the sine function from either side, heading towards 0, the x-coordinate 0, what is your y-coordinate doing? It's getting closer to 0, right? And if I write it from the left, what happens? The same thing, right? Okay? Well, why does it make sense that this graph climbs if I move like I normally do to the right from 0? I want you to make your argument and justification in terms of the unit circle. Why, when I take this picture, this graph, and ride the function, leaving 0 and going away from it, why does the graph climb? Why does it climb, peak, and then fall again in terms of the unit circle? Well, first of all, if I start right here, where on the unit circle am I? If I start at the origin,
0, 0.
I'm at 0. I'm not at 0, 0. On the unit circle, I am where? At 1, 0. And then if I trace the circle, what happens to my x values? They get smaller, right? What do my y values do? They get...
Please send 201 to 240 for elite plaid deployment at this time. Please send
Was that elite
201
plaid?
to 240.
I believe it was. We could talk about that for days, right? That's what preps wear, elite plaid. Okay, that's... You like that, Todd? Okay, so back to the unit circle. So and what are the y coordinates on the unit circle? What do they give me? Sine cosines, people. What do the y coordinates give me? The sine values, yes? What do the cosine come from? Cosine comes from x. Hallelujah. Maybe I'm getting something out of you. All right, so now that I've all but told you the answer, tell me why this graph climbs. Because the y coordinate gets bigger as the angle, which is what your x coordinate is on the graph, right? As the angle gets bigger, yes? To a point. At what point does that change? At 90 degrees or pi halves, right?
Yes.
That's where the sine graph peaks, and that's why that peaks, yes?
Yeah.
Okay. So we're looking at this sine x over x function. So my numerator, as x approaches 0, for the sine graph is 0, right? What does the denominator do? Well, no, I'm saying, what does the numerator is the parent function sine x. We've talked that to death. I didn't think we needed to talk the denominator to death because it is y equals x. Yes? What happens with x the closer I get to 0 from either side? It becomes smaller. Smaller from either side?
Yes.
No. No, it doesn't. It gets closer to 0, but that doesn't make it smaller because if I'm moving towards 0 from the right, my x values are getting bigger because the function gets bigger everywhere. Yes? Okay. But if I plug in a really tiny number, let's say 0.01. Tiny enough for you? Okay, 0.01 would be 1/100th, yes? What do you think the sine of 1/100th would be? This is not a trick question. It wouldn't be 100th, but it'd be very tiny, right? It would be close to 100th. Why would we expect really close to the origin that the sine graph is going to give you, the sine function is going to give you back whatever you give it? Let's take a little pause here. And during our little pause in our conversation, I'd like for you to grab your calculators and graph the sine function and the line y equals x. No, don't tell me now. Graph the sine function and the line y equals x. Because I've taught y'all, I've all but nudged you right up to the answer, and you're staring at me as if I'm speaking some foreign language. I'm speaking pre-cal. Please, God, help me tell me that is not a foreign language to you. How about as y'all come and go, don't shut the door. Because whoever unlocked my door didn't really unlock it, they just opened it. All right? So we're going to tab. I'm going to go up here. And we're going to... Y'all got it?
Yes.
Okay, maybe I'll stop because I need to play with this till I get better at it. What did you come up with? What do you see on the graph? You should see on the graph a picture that makes you understand why I'm agitated with the fact that y'all can't answer basic questions about this relationship. Because I showed you this last year. Do you not remember last year when I graphed these two functions and I zoomed in? What happened when I zoomed in really tight? They look like a line. They look like what line? Y equals x. So the closer I am to 0 on the sine function, what do I know about the line y equals x as opposed to the function sine x? They're in essence the same. So what does that tell me? That tells me that in that really tight little interval, and it can be like you could have to have a microscope to zoom in to find it, but on that tiny little interval that a limit would be looking at, because limits, we're talking about...
Just please send 241 to 280 for laptop deployment at this time, 241 to 280.
When we're talking about limits, we're talking about very small little regions of the function. And that's why, we talk neighborhood, intervals. We're talking about a very tiny little spot. And if you zoom in on your calculator, you could do the same thing. Close to 0, they basically look like the same function. Okay? Now, the significance of that is, let's rewind. On the line y equals x, what do I know about every single coordinate on that line, even the ones I don't normally plot? The coordinates are the same, right? Okay. Well, if the sine function in the center of the graph mimics y equals x, what does that tell me about the sine of really tiny angles? It's the same as the value of the angle. Do you see that logic?
Yes.
That's the power of what you know. We're just you haven't learned how to put it all together yet, and this class forces you to do that. Okay, so now let's go back to our limit. The limit, under discussion, and you've already got this written on your paper, the limit as x approaches 0 of sine x over x equals 1. Tell me why. Go ahead, Josiah. You had an aha. I want to hear it.
Because the numbers are the same.
Because the numbers are the same. All right? When I plug that tiny little number into the top, what am I going to get back? That number. When I plug that tiny little number into the bottom, what am I going to get? The same number, right? So if I got the same number on the top, no matter how weird, ugly, tiny it is, and the same number on the bottom, what do I get every single time? 1. Now, I told you all that so that for the people who are thinkers, you will remember this limit because of this conversation. For the rest of you that are like, I have no idea what's going on, and I'm not going to say so. Well, you just deprived yourself of your education, and you'll just have to memorize this. You cannot memorize your way through this course, though, so be aware of that. All right. Whew. That was a workout for Twitty. Too early in the morning. All right. Our first theorem. I will abbreviate all theorems with THM because that's what your college professors will do, and if you ask them what that means, they're going to ask you to leave. Or otherwise, just make you really wish you could leave because they make you feel like an idiot. All right? No idiots leave Twitty's room. All right. Properties, and we're going to abbreviate that. Props of limits. All right. If, and we need this if up top because we're going to use some different letters in this definition, okay? Capital L. And for those of you that like to just arbitrarily, I feel like making capital letters today. Oh no, I'm going to write everything in lowercase. You can't do that anymore. We've got capital L, capital M, lowercase c, and lowercase k are real numbers. Now, I'm going to ask you not to have your book open for this, or if you do, to like flip the page or something so you can't see it, okay? Because I'm going to talk you through this because the notation can distract you, but I'm going to talk you through the meaning of each thing so that it will make sense, okay? Now, these properties are a little bit tedious to have to write and talk about for a few minutes, but they are extremely helpful in understanding that it's just this simple, okay? It's like I told you. The theory behind it is complicated. The wording of this, or well, actually, the computation of limits is generally pretty simple. All right. So, I'm going to pause right there and have you tell me what that means. And I didn't even read it out loud so that you'd have to tell me what it means.
That is C under limit.
Closer what gets to C? X. From which direction? Both. Both. And that's new. We'll talk about that more in detail later. But the closer I get to, the closer my x value gets to C, go ahead. The y value of the function gets closer and closer to L, which is the limit. Okay?
Teachers, please send 281 to 320 for the elite class deployment at this time. That's number 281 to 320.
Oh, thank God they left off that she didn't say the elite pad thing twice. Yeah, I know she said plaid. She sent her little plaid flag. See if she can say that 3 times fast. Plaid flag. Trying to interject some humor here. All right, so what does this one mean? For g of x, whatever that function is, right? All right, so what they've done for you here is we have limited the understanding of capital L, capital M, C, and K to be, and actually that should be a K, and actually they put C. All right, but those are real numbers, right?
Yes.
The closer I get to that C value for f of x, the closer my y value gets to L. The closer my my x gets to C for g of x, the closer I get to big M. Okay? That's just some other number. So L might be 12 and M might be 14. Okay? Just pulling random numbers. There's no significance to the numbers. All right, so no. No, because it's like 2 different functions. So like f of x might be x squared and g of x might be x cubed. Okay? All right. So the first rule is the sum rule. That is SUM as in addition, not sum as in, pick one. All right? Now, your book has this written in words. We're not going to write the words down, but you can skip a line to come back and copy that in if you want to, but I'm going to get you to tell me the words based on our discussion of the symbols so far. Okay? You ready?
Yeah.
You're terrified, aren't you? Admit it. All right. The limit as x approaches C, parenthesis, f of x plus g of x equals, all right? Well, what does that mean we've done? We're not just taking the limit of f of x, and we're not just taking the limit of g of x. So if f of x was x cubed and g of x was x squared, what would this actually say? It'd be the limit of x cubed plus x squared. So that's what they're talking about here. So you add the functions together, right? All right, well then the rule tells you this is L. I don't get my letters mixed up and totally confuse you, so I'm going to be double checking the book. So what does that say? All right, so this means I have taken the limit of a pair of functions, right? Of the sum of a pair of functions, right? That's what this means. Y'all with me? And what was L? That's the limit for x. I'm sorry, f of x at C, right? And what was M? For G. So I'm going to start a sentence and you should finish it. The limit of the sum of two functions is the sum of the limits. Isn't that easy? Okay. Don't take time to write that. It's in your book. You can come back and copy it later. I want to move along. So let's try rule number 2. I did? Yes, I did. Thanks. Keep me straight. It's weird not looking up there, and I'm writing kind of large there too, so I'll fix that in a minute. If you're interested, I'll show you later how I have to do this, okay? So I'll tell you what. Let's put slash. In fact, we're going to cross that out, put a little 2 under here. I'm going to cross it out. You can erase it on your paper. And we're going to abbreviate difference rule. In fact, let me do this. Let me change that color to make it obvious what I'm doing here. Just going to save you some writing time. And I don't have room to write rule, but write difference rule out there to the side. So we're going to make this the sum and difference rules. All right? Now, I'm going to come in here and put a minus under the plus. So what does that say? Plus or minus, right? So if I have f of x plus or minus g of x, then that makes the limit plus or minus L and M. So I'm going to start you off and get you to finish the wording, and I'll give you time to tidy up those two rules before we move on to Rule 3. So you can go get your elite plaids. Apparently we're all going to be preppy by the end of the day. All right, the limit of the difference of two sums is the difference of the limits. By Jove, you are catching on. All right, we're moving on to the other screen. I'm going to make this a little smaller so it's a little less jarring to look at. It's like I'm screaming at you. Giant font. All right, product rule. By the time I write the second or third one here, you should be almost writing ahead of me. Because a product means we're multiplying, right? So now we're talking the limit as x approaches c of, and I don't really need parentheses here because I'm multiplying the things, but I'm going to put it here for, like, emphatically, of this one thing together, this product, okay? The limit, and I guess I kind of do need the parentheses, but we'll talk more about that later. All right, the limit as x approaches c of f of x times...
Teachers, please send 321 to 350 to the elite pad deployment at this time.
Didn't forget my parenthesis on that one. F of x times g of x equals, do you want to take a guess? If in a perfect world, what would it be? L times m. So the limit of a product of two functions is the product of their limits. Now, what do all these rules? Are you getting the import of what's being said here? If I have a complicated looking function that's made by combining through, so far, addition, subtraction, or multiplication, what do these rules allow me to do? They allow me to take the limit of each piece separately so that I don't have to do it all at once. Does that make sense? Okay. Which is also what allows us to do term by term on things like polynomials. All right, number 4. Rule number 4 is the constant multiple rule. What is a constant?
Stays the same.
That's what 4th graders would tell me. To a math student, what is a constant? Really, people? It's a number.
Oh.
Smack yourselves. At least once. Oh, Lord. Just a little refresher from the top of this box of rules here. What's K? It's just a number. Keep that in mind. All right, so the limit as x approaches c. That's going to start off all these rules. Of K, f of x, equals, anybody want to guess? K times L. So the rule is the limit of a constant times a function is the constant times the limit of the function. I was just, there's all like this, you like the entire class practically looked at me with your mouth kind of half open like you're about to talk and you're like,
I thought you were.
and then you started, and then it was in unison once you started. Y'all are so.
We have to synchronize.
Is that what it is? Is that what it was?
We went on.
Y'all are like ants, you know when to bite?
We went on a group meeting. There was a.
You ever notice that? Like, you won't know your foot is covered in ants until they all bite you at once. It's like, how did y'all do that? The miracles of God's creatures. Number 5. Quotient rule. What's the word quotient mean? We're going to be dividing something. All right, now, remember, every time there's a rule about any kind of quotient, what do you always have to have at the end as part of the description or definition? Never mind. Because Todd just looked like somebody held a gun to his face. So I'm going to stop. I actually was, but we'll get back to that. The limit as x approaches c of f of x over g of x equals, what do you think? L over m. You think that's always going to work?
No.
Why not?
What
What did you say? Michaela, well said. And I've been meaning to ask you, is that a birthday badge? We will sing to you. But we'll wait and not record it.
We should record it. That's a good clue.
We'll do the RN version of happy birthday. All right. So this is the part of the definition to which I was referring. We have to make the condition that the denominator is not 0. So m cannot be 0. So this rule says the limit of a quotient of two functions is the quotient of their limits.
But x equals 0.
Yeah, provided that the limit of the denominator is not 0, right? Because you can't divide by 0. But that should be sort of obvious at this point, shouldn't it?
Yes. No.
As I used to in geometry call some of the theorems the duh theorem. Duh. All right, power rule. And this is the last one. You're welcome.
Okay.
Teachers, please send 351 to 400 for a leak pad deployment at this time. That's 351 to 400.
Okay.
Where do I go?
Just go down this hall until you run out of room, and they'll be down there waiting for you.
You can see. Look for the big boxes.
Do they still have the boxes up like
Yeah.
your cattle going through a... like you're about to get God knows what done to?
We couldn't figure out how to get to Coach Falkenberry's room through the box.
Yeah, I think I had to go down there for something after school, and they hadn't moved the boxes yet. I'm like, guys, it's over. Let's move the boxes.
I accidentally caught one of the boxes on fire.
I don't know. But I'm sure whoever thought of it is quite proud, and the rest of them are quite thankful that someone thought of it.
They like blocked off Falkenberry's room so nobody can see. And then we got yelled at because we were all standing outside his room.
How dare you? If R and S are integers, I am frightened at the possibilities of the answer here. But what are integers?
Numbers on the
What?
What are integers? Whole numbers
Greater than
and
0.
their opposites.
Opposites.
So like 2, -2, 3, -3. Okay.
Oh.
Are integers. And S can't be 0. Then, I had to have a preface for this one. And that says then. Just trust me. All right. The limit as x approaches c of inside parentheses f of x raised to the r over s power. Now, if you've caught on to the pattern of the simplicity of the pattern, I should say, of these rules, what would you just ballpark this one to be? And you are correct. R over S. And underneath there, put in parentheses, as long as L raised to the R over S power is a real number. So the limit of a rational power, now a rational power just means you're raised to a fractional power. And if that's true for fractional powers, what do you think it will be for other things? True. Because remember, a rational number just means you can write it as a fraction. So if I have a function squared, my new exponent, I could think of it as 2 over 1 to emphasize the fact that this function still, this rule still applies, right? You with me? So really for any exponent, all right? So the limit of a rational power of a function is wow. Okay, let's run back through all of them, and then we'll come to a grand finale with this one, okay? The limit of a sum of two functions is the sum of the limits of the two functions.
Yes.
How about the difference? The same thing. So the limit of a difference of two functions is the difference of the limits of the two functions. The limit of a product of two functions is the product of the limits of the two functions. Okay? The limit of a number times a function is the number times the limit of the function. All right, only one more left. Oh no, I'm about to forget quotient. The limit of a quotient of two functions is As long as? Very good. The denominator is, the limit of the denominator is not 0. You with me?
Yeah.
Now, the limit of a function raised to a power of the function raised to the power, and there is the distinction here that the s, the denominator of that exponent, cannot be 0. Any denominator can't be 0. You with me?
Yeah.
All right. I know this is long and tedious. I'm gonna stop this video and restart it, so bear with me.